Uh, Thank you, Deval. It's a great pleasure to speak at APEC. So today I'm going to talk about MagNet Challenge, which is a project which I led together with Professor Charlie Sullivan in the past couple of years. And the goal is to connect people, magnetics, and AI together. So if anyone have worked with Charlie, you know that if you have him on your team, you just don't have to worry about the technical side. You have to be converting yourself into a salesman. And that's what I'm doing here. So I created a logo, come up with a name, organize the MagNet Challenge, and now I'm going to do a salesman pitch. First of all, let me acknowledge everyone who have contributed to this project. When I'm speaking, I'm actually representing a community of people who think we should fully embrace AI in the design process of power magnetics. Of course, Professor Charlie Sullivan, we have outstanding grad students and postdocs working with us, collecting the data, running the challenge, evaluating the models, and develop benchmark models for the challenge. We have an outstanding, excellent judge committee. They really put a lot of time and efforts in helping us setting up the rule, develop the evaluation criteria, looking at the teams, and then select the winners. And finally, there are a lot of friends and people who have supported MagNet Challenge from the very beginning. Believe me, I can't list all of them here, so I intentionally make the name very, very small. So don't look for your names there. So I just can't list every one of you here. So the MagNet Challenge ran for 4 years, starting from 2023 and then 2022 to 2026 until now. So really, we have combined together, we have participants from over 21 countries, 58 universities, 80 teams combined together. More than 238 students participated. And then the overall processes for the 2 challenges last for 48 months. And then we have participants, very good participants from US, Asia, and Europe. But unfortunately, even we tried very hard to reach out, we still don't get any teams from Africa and Middle East. And that means in terms of technology spreading in this particular time, it's still very important for us to spread the technology and encourage more students to participate. So finally, this is all the teams participating in the challenge. I'm actually fortunate that we organized MagNet Challenge before the AI agent come to true, because now if we organize the MagNet Challenge 3, we have to worry about whether there are real person behind these teams, because this is a very well-defined software engineering problem end-to-end. So I'm very likely true if anyone is going to host the MagNet Challenge 3, very importantly, we have to really draw the criteria how much you can use AI to participate in this kind of challenge. We're quite fortunate to rule it out before the real AI agent coming through early this year. So finally, I want to acknowledge all the funding agencies. So the data we use to run this challenge come from US governments. It's the taxpayers' money. If you're paying US tax, you contribute to MagNet Challenge. So we thank APEC and NSF for sponsoring the challenge and allowing us to open source the data and allow the data to be used by researchers around the entire world. I think this is very important in terms of the research spirit. We thank the US government and US taxpayers for supporting the research. We also thank IEEE Power Electronics Society, Princeton University, Dartmouth College for providing the administrative support, Brianna and Mike Kelly specifically. And finally, the many industry sponsors who supported our work. Important thing is not about money. It's actually allowing me to put the logos here, because that sends a message to the next generation of engineers. This is what industry care. We care about how do we embrace the advanced technology into power electronics design, and the students really get motivated and participated in the challenge. So let's come back to technology. Why are we interested in doing magnetics with AI? So it's actually sort of when you're doing 5-year project like this, you need some motivation. Like we're at Princeton University, the best thing we do is we can get Nobel Prize. So we want to find a way to tie ourselves to potential Nobel Prize winners. So actually, magnetics, of course, comes first. And then there's Ising model, which is a branch of statistical physics model, trying to describe how does a large number of magnetic beings work together. And around 2024, this Nobel Prize in Physics was awarded to Professor John Hopfield and Geoffrey Hinton. So they were awarded for their fundamental contribution in defining the fundamental mechanisms behind neural networks. And we were going back and reading their papers, and we were fortunate to find that they both mentioned magnetics. Their inspiration of developing modern neural network model come from statistical physics, which is also describing a large number of units, uncertain units. You can't model each of the spin, but you can model the statistical behavior of the spin. It's very similar to the neural network. You can't even understand which parameter is doing what, but when you group all of them together, you can statistically understand how it's behaved. John Hopfield the contribution was energy-based neural network, describing how does neural network converge to the lowest energy state, which is related to how magnetic spin converges to their lowest energy state. And then the contribution of Geography Hindem was backpropagation algorithm, describing how does the neural network algorithm converge by introducing a loss mechanism. That's sort of related how magnetic core loss relate. When you spin fighting with each other, you create loss, and this loss is the mechanism which leads to convergence of magnetic spin. It's a very interesting story in history that ties magnetics with AI. Studying magnetic material do inspire the development of modern AI, and vice versa. We're trying to leverage modern neural network to understand the physical phenomenon. So a little bit more about history. This is about power magnetics, because magnetics is a huge domain. There are a lot of different types of magnetics. Power magnetics is a branch of it. So when we first think about power magnetics, we think about transformer, the big, gigantic transformer, power transformer. And then we have, around 1980s, you have this cartoon transformer where my son, kids know about it. Right? It's very powerful, very versatile, can change its shape. And then around 2010, or even before that, there is a first wave of neural network. That's where the feed-forward neural network was coming. And actually, there were a group of researchers who tried to apply neural network to describe magnetic behavior, but with limited success. And the reason behind it is because at that time, neural network was not mature, and the computing power was not ready. So that's actually the first try of using neural network to model magnetic material. And later, around 2017, that's where the transformer coming. That's the neural network transformer, where Google's famous attention is all you need paper pointed out is a very versatile neural network structure that can take sequence, language, can take image, and take high-dimensional data if you have many data coming from multiple domains. So that's what really lead to the modern large language model or modern AI. And then around the same time, a group of researchers start to talk about AI for science, right? Using AI to model different type of materials. And then we were sort of at that time, many of my colleagues were talking about, let's do it. Everybody's talking about AI, let's do AI for magnetics. What we find is after 3 years, the AI for chemistry or AI for protein people, they won the Nobel Prize again. Right? It's AlphaFold when it's really solving a fundamental problem in understanding protein. How does gene was translated into protein? And we're still running MagNet challenge. But we're proud enough. We're making sufficient progress, and we still see a huge potential over there. And finally, recent year, we have this powerful AI, which is, again, very important wave. And fortunately, we're seeing a lot of discussions coming from previous speakers where we need solid-state transformers, we need integrated voltage regulators. And the bottlenecks for both solid-state transformers and integrated voltage regulators, which power the future of AI, the bottlenecks is in magnetics. And hopefully, we can use the tools we developed by AI for modeling magnetics to improve the power electronics needed by AI. So why do we have to do it, right? For me, as a power electronics engineer, I feel twofold. One is responsibility. So it's our responsibility to develop AI tools for magnetics. It's not going to happen automatically. The VLSI people, the RF people, the analog people, the mixed signal people, they don't really deal with magnetics like what we do. It's our responsibility. It's everyone sitting here. It's our responsibility to fully embrace AI and model power magnetics and develop tools to make it mature. If we don't do it, it's basically we're not doing our job. And second, there's a huge opportunity. Right now, I'm sort of like an NVIDIA employee. I listen to Jensen Huang's podcast all the time. So he always talk about this vertical integrated and horizontally open, right? So AI is really all the way go down to energy and all the way go up to all type of application. Magnetics is similar. Magnetics is a domain which is also vertically integrated and horizontally open, right? So we go all the way down to materials and physics and all the way go towards up to the application. We're also horizontally open, right? Designing magnetics for IVRs, designing magnetics for solid-state transformers are completely different. So it's really a very interesting area where I can see artificial intelligence play a very important role, all the way down to how do we discover newer magnetic material, guiding the manufacturing process of magnetic material, either in a very, very small scale, integrated voltage regulators, or very large scale in solid-state transformers, and at the same time developing better tools to model the nonlinearities in the materials so that we can come up with better design. So how do we do it? Like now it's our responsibility to do it. How do we do it? It's to learn from other people. Like AI is actually a language which connects many domains together. It allows us to talk to people, our neighbors, our colleagues in the same department in a common language. So how do we learn? How do we do it? So we learn it from the Computer Vision Society, which basically cultivated the recent development of AI. Many of you probably heard about MagNet. It's a huge, large-scale database developed by Professor Fei-Fei Li at Princeton University at 2006, which is a magic year. It's also the year where NVIDIA started doing the CUDA technology. So that's basically a very simple concept. Now we're going to do AI to recognize image. We need a standard, large-scale, high-quality database that everyone can come and compare their models. And that's what led to MagNet challenge. So they realized that with a single group of people, you can't do too much. You have to unify the people around the world which have the same motivation, same mission, same vision as you to work on the same problem. So they open sourced the database and run this challenge, which attracted Professor Geoffrey Hinton with his students, participated in the challenge, and developed a neural network model which beat all the traditional, original logic-based models. So that's sort of like the history of ImageNet, and then the rest is all coming through. We have AlphaGo, we have Transformer, we have ChatGPT, and this year we have OpenClaw. So what I want to say is actually take 20 years. The history feels short, like 2006 is 20 years ago. It takes 20 years for the frontier AI people to really have an impact that everybody can feel. So if we count MagNet 0, like the time when we started Magnetic Challenge, it's actually slightly before 2020. We counted from 2020, 20 years from 2020, that's 2040, right? So I'll throw this out. I talked with this with my students. Before 2040, 70% of our magnetic component could be designed by AI agent. I don't know, this could be a good debate among all of us. I don't know if it's too early, too late, 70% is too much, probably 50%. I guess we can leave this question for tomorrow's debate. Do you think before 2040, it will be possible for us to have 70% of magnetic component generated by AI? So about a specific technical challenge, so we run a 2 challenge. We want to design a challenge so that it's so easy and simple that everyone around the world with a computer can do it. And at the same time, we want to make sure the problem is difficult enough so that the winners can have high impact and have the motivation of really fundamentally change the way how we design and think about magnetics. So we select Steinmetz equation, which is probably the oldest topic in magnetics, right? So you basically model the core laws with 3 parameters. And it's, of course, everybody understands it's not accurate. It's probably more than 100%. I do have design examples. When I was a grad student, you design it and measure it, you have more than 100% error. It's basically modeling it doesn't make sense, right? So Steinmetz equations, our first target, 100 years old. We're very confident that we can find a better model with machine learning and neural network. And second is transient. We have reasonably good success in trying to replace Steinmetz equation. It's done. And then the second is we go for 50-year-old equation, which is precise model, and geostatistical model, very old model, trying to model the hysteresis loop. We know the BH loop, change with frequency, amplitude, temperature, waveform. How do you model it? How do you collect enough data, train a model so that for an arbitrary wave, for example, in a PFC, in a power amplifier, in an envelope tracker, in wireless power transfer system where your system is dynamically changing, how do you more precisely model the loss? So I'm not going to show the technical details of how much we can do better, but I want to tell you, if you are a company designing magnetics for PFC type of magnetics, we have examples where if you only use IGSE or use a more precise machine learning or AI-based model, you can easily reduce the loss by 30% to 50%. That means perhaps the magnetic component can be 30% or 50% smaller, or maybe you can reduce the heat sink or improve your other design metrics. That's the impact we have. And then specifically, I want to talk about what's important, what are the lessons we learn. Right? The first thing we need to do when you want to embrace AI in the design process is to think about data. Data, data, data. It's extremely important to get high quality data and organize the data in a good way, and also formulate a problem where the AI can take. I believe that in the near future, that's where human designers can contribute. If you want to embrace AI, is to deeply think about data, think about how do you collect the data most efficiently, and think about how do you convert the problem that you know in the data problem into a problem where AI, machines, large language models can understand. And there are also great examples. We leverage great examples. There's WordNet, which is a big database for language. There's ImageNet, big database for graphs, pictures. And then we have MagNet. The only thing in common is that all three of them are invented or developed at Princeton University. Apparently, we are sort of like free enough in doing boring data collection efforts. But probably that's sort of the important thing. Whenever you want to do AI-related problem, whether it is a company or university, start from data. So we're very proud to say that currently we maintain the largest open source MagNet database in the world, because a lot of companies don't open source. Right? We probably were happily owning this largest open source database situation. I hope somebody will beat us in the near future. And then we currently cover more than 20 commonly used MagNet material. We have a fully automated system which is getting replicated in many places in the world. And we have more than 10 hours of measurement time. This is not including the time we use to check the data, improve the quality of the data, and organize the data. The second is the data quality. We do have really good postdoc researchers, Diego Serrano and Thomas Grillot. Diego is currently working for Wolfspeed, and Thomas is going back to Zurich, starting a new career. So really good, I want to mention their name is, again, data quality is extremely important. AI models are garbage in, garbage out. The quality of your model will be just as good as the quality of your data. So that's very important. Whenever you get the data, make sure you think it systematically. How do you analyze statistical data? How much error comes from statistics? How much error comes from systematic error? How do you trace back the error? How do you filter out the outliers? And how do you understand the limitations of the data? Because you can't collect all the data available in the world. Like, when will this data be available? When will this data be applicable to the particular application that you're targeting? All of this is actually where human designers, when the models are almost ready, you can get infinite models from GitHub. But now it's what human designers can really do is think through it. How do you get data, and in which cases this data is useful and applicable? And then this is probably the most technical slides. I'll try to explain it carefully. So philosophy behind MagNets. How do we convert a traditionally domain-specific problem into a data problem? So we went through many paths. I'll explain it in the most straightforward way. I would say there's an opportunity to change how we think about power electronics design from sort of like linear assumption, linear simplification of RLC with switch and combine them and try to interpret our human brain into sort of like time sequences analysis or token. So if you think about any power electronics converter, you have some input energy getting into some kind of circuits, and you produce some kind of output voltage, right? So output energy. And you use some of the, if you think about switch network, it's just excitation circuits. And it's producing some excitation and feeding it into passive components, inductors, magnet transformers, capacitors, or piezoelectric components. These are memory devices, right? In computing, you have these computing cores and memories. In power converters, you have these switching circuits, which generate excitation and pass it through the passive components. So generally, in human, we try to understand everything with a linear model, right? That's our limitation. We cannot manage very high complexity. But with AI, we can manage very high complexity, and we can capture all the nonlinearities and complexities in the passive components, in saturation of the magnetic material, in degradation of the capacitance with DC voltage, and everything. So this is actually representing an opportunity to think about processing power electronic circuits with simplified linear circuits into processing energy as token, and then capture those complexities in the memory devices with artificial intelligence. And then in large language model, what do? A lot of systems look like this. You have some previous states where you have some internal states which stores energy, that's the passive components, and if you have some new excitation coming in, how do you convert it into the new responses? And that's actually how we framework the MagNet challenge, especially MagNet challenge 2, is we give the student teams the historical data where the MagNet material is going through. We give them some current states, and then we give them some future excitation and ask them to predict the future response. So that's an example of converting a way of thinking about power electronics into a way where sort of AI, modern AI, is very good at processing. And then the rest is all kinds of trial and error. I would say in the AI stage, again, in analytical model, we try to find the ultimate best solution. But in data-driven methods, like human brain, probably is not, if the problem is complex enough, there's not that only one most elegant solution. Many solutions coexist, and you have to allow people to try and error. That's the same thing happening in large language model. If you ask the OpenAI or Anthropic, well, is this the only way of developing large language model? Of course not, right? So we have to change our mind where for data-driven research, trial and error is actually extremely important. It's very important to engineering and data so that you allow more and more people and more collaborators and companies to try and find the best solution. And the other thing is it's very important to find collaborators, right? So we are PELS, we are Power Electronics Society. We solve our mini problem. And then the next step, I'm sure Magnetic Society, IEEE Magnetic Society is looking at magnetics plus AI. We're actually launching some collaborations with them. And if we go one step further, the Solid State Circuit Society, the Circuit and System Society, there are many other power electronics communities are thinking about similar problem where how do you transform or teach AI to really understand KVL and KCL and how do we design circuits? And once we solve all of these domain-specific problems bottom up, we understand magnetics, understand capacitors, understand RF components, understand piezoelectric components, understand circuits. Then we go back into the general intelligence player where they are developing large language model, trying to understand the entire world. That's our vision. What can we contribute in these data eras? Apply our domain knowledge, try to address problems one by one. Especially humans are the interconnect between the digital world and the physical world. And again, we need both, right? Humans, we need simple and elegant and models that our brain can manage and allow us to interpret, versus the machines can really manage huge complexity. The models can be very accurate, very sophisticated, and can be high dimensional. So all of these models, from very simple to very complex, will coexist, and then that will greatly accelerate the design process of power electronics. So the next is all the results. This becomes a MagNet World Cup. As I mentioned, 21 countries, student teams coming from 21 countries participated. What we do is you can't ask them to compete for one metric. The world is multidimensional, so we go with two-dimensional. One is we care about the accuracy of the model, and the other is we care about the size of the model. The accuracy or error, the lower better. The model size, the smaller better, because if you have the smallest neural network which achieve the same accuracy, that means your computing can accelerate faster. Your design can be more rapid, and you can integrate the algorithm with SPICE or finite element modeling to accelerate your design. And then on the right-hand side, it's actually the XY graph of all the student teams in terms of model size and model accuracy. And you can see the Pareto fronts, right? The Pareto fronts is where the models tend to have relatively high accuracy and at the same time small. What I want to highlight is that at Princeton, we don't participate in the challenge, but we're very interested in where people can do better than us. Right? So we have our secret model, which we developed together with the student team, and we found that we are sort of sitting in the middle, and the winning teams are either 10 times, the models are either 10 times smaller than us in terms of model parameter size, or 10 times lower error than us. That shows the power of collaborative research, right? In the data era, you're not doing research with your single team. You can only do this much. But if you open source the data and allow other people to collaborate and compete, that's really advancing and really allow us to see the entire Pareto front of the technology and figure out where the bottlenecks are. So these are the winning teams. I want to give them a shout. So we have two track. One is on performance side. The other is on the the side student teams from over 9 countries were acknowledged in this competition. So we are going to have an award ceremony very soon. So you're welcome to come tomorrow. So you interact with students. These are the next generation of students who are really interested in embracing AI. Maybe companies want to hire. And also, what happened next? There are many directions. We can go towards physics. We go towards SPICE. Go towards finite element modeling. Go towards AI agents. And there are student teams exploring all these directions. I'm going to skip all the highlights. Georgia Tech, Paderborn. They are doing magnetics with physics. Fuzhou University, Hong Kong University, City University of Hong Kong, and Xiamen is doing magnetics with SPICE, integrating neural networks with SPICE. There are also finite element models with Fuzhou University and Hong Kong USD. They are diving towards that direction. There's also a startup company called InSim trying to explore AI with finite element modeling to get better results. And finally, AI plus agents, that's coming. I'm pretty sure within 1 or 2 years, I can't predict, probably tomorrow, there'll be a new model which is capable of really automatically trying all different designs in power electronics. So I want to thank all the people who contribute to these efforts. And finally, this is the last session of the APEC plenary. I hope everybody enjoy APEC. And I put Professor Kasakian's in here. APEC is where magic happens.
Thank you, Minjie. Questions for Minjie? I think it was a very interesting presentation. I'm sure people have questions. I don't see, I can't see. Yes.
Hi. First of all, thank you so much for the really clear presentation. My name is Nicola. I'm from ETH Zurich. I'm from the AI side more than from the electronics side, and the slide where you were making the comparison between transformers and magnetics is really interesting to me. Respect to transformers, aren't the networks in this case also conditioned on the magnetic material? So isn't there an extra latent variable that you need to include in the process?
So I guess this is a very deep technical question about why do we want to use transformer as the model to model magnetics. No, that was not our intention. It's just like I'm trying to make an analogy. Like there's a connection between transformer and magnetics. But of course, the winning models are not using transformers. They are using many different types of neural network architecture, including GRUs, LSTM, and feed-forward neural network with feature extraction. They are also hybrid physics-informed neural network structures. That's the beauty of running this as a student challenge, because from the organizer perspective, we don't know what is the best model, and it's really open to the community to figure out the best way to model magnetic material.
Thank you so much.
There's a question on this side. Yeah.
Hi, can you hear me?
Yes.
Hi, this is Nick Kirkby from Arizona State University. My question is about a statement you made about during your PhD research, you used the Steinmetz equation to predict loss, and you were off by 100%. I'm wondering if you could comment on whether that was model-induced bias or underlying data-induced bias. Thank you.
So I would say it's a mix of many things. First of all, when you are using Steinmetz parameters, like whether you use a local Steinmetz parameters or global Steinmetz parameters will make a huge difference, right? So there are different ways of figuring out the parameters. Second, Steinmetz equation, usually you have to do curve fitting. They don't give you the exact frequency you are operating at. And it's only for sign, and only with a few data points for temperature, right? So if I'm happening at one particular temperature and with a frequency that the data sheet doesn't cover, that's where the case. If you measure the loss, it may give you 1 watt. And then, if you predict the loss, it may give you 1 watt. But if you measure it, it may be 2 watts. So that's what I caught as 100% error, because it's a 2 minus 1 divided by 1. Right? So that's the case where, as I said, it comes from both. You don't have the data available, and the data doesn't cover the operating condition that you care, like with DC bias and temperature.
Okay, we'll have one final question here.
Hi, Mike Arison with Ferri Products. So very interested in the material end of it. You mentioned using this for developing new magnetic materials. And I was wondering if you could speak to how close we're getting to the physics, rawest, smallest understanding of these crystalline structures set up the following domains that have the following properties to really accelerate the development time of new materials.
Yes, I can comment on that. So as far as I know, there's a separate community of people who is coming from the atomic level or molecular level. They are running these chemistry simulations, fully computational chemistry to understand magnetics. So I would call it like that's the bottom-up approach, which more fits to what you are explaining. Okay, how do we really understand the fine-grained physics? And we are coming from a designer perspective because there's a huge gap between the atomic material level behavior and the component level behavior. So I would say we are sort of looking at the problem from both ends, and both ends has its value. So how far away, I don't know. I feel like from design perspective, it's more of a clear path, low risk path. But on the other side, whether somebody will be able to use AI to discover new material, I don't know, and I cannot comment on it.
Thank you.
Okay. Thank you, Minjie, for a wonderful
Thanks,
presentation.
By the way, if you need a T-shirt, go to the exhibition hall. Charlie may be there.
Yeah. So we have a salesman professor, so he's giving you a reason to go to the expo hall to get the T-shirt. So thank you for coming today. The reception in the expo hall starts now, and we'll see you all there. Thank you very much. Enjoy the evening.